In this video, we're going to finish off our work with Taylor series and the idea of how you can use polynomial terms to approximate a function. This was the series we saw kind of in the middle of our notes last day, and it just adds more and more terms to it, more and more derivative terms to it, higher derivatives, higher order terms, people might say, and we're going to try it out with just a couple more examples here. We did this Taylor series for sine. Technically, I guess you could say it's a Maclaurin series because it had a nice x value of 0. And we're going to do a Taylor series for e to the x now. Also, again, I guess technically a Maclaurin series because I like to do a nice x value of 0 again. It's a nice place to start evaluating this function. And we'll see what happens when we start evaluating the function and its derivatives at x is equal to 0. So at the beginning, and this is how you do begin your Taylor series work, you just start evaluating the function and its derivatives at that point. So the original function is just e to the x. And if I go and evaluate that at this chosen point, so somebody chooses this point, or maybe you do, depending on how this deal's going, and you say, okay, well, what's happening at x is equal to 0? Well, the function's equal to 1. Okay, great. Now let's go and do a derivative. What does the first derivative look like? Because we looked at the green one, which wasn't a derivative, or the 0th derivative. Now the first derivative. Well, it's also e to the x. So when we go and evaluate that at this chosen point, I also get a 1. I'm going to do this just 2 more times, and then after that, we're going to be kind of sick of it. Second derivative of the function would be e to the x again. And of course, then the second derivative figured out at 0 would still be a 1. And one more time, just for good luck here. If I did a third derivative, yeah, nothing's new. It's still e to the x. And that third derivative then evaluated at that nice point is a 1. So when you do these, you're going to first have to find, well, what does the function look like in terms of its derivative? And then what does it evaluate out to, right? So on the left, I'm just looking at those functions, the derivatives. And then on the right, I'm actually evaluating it at that one nice point only. Now then, the series for e to the x, what's it going to look like? Well, if you actually try this out, you can say, hey, you don't want to work with e to the x? Let's work with some polynomials instead. If I go with the 0th order term, the 0 term, the first term, I guess, that physically shows up, that would just be that green 1. Okay, so I'd have the 1 there. Okay, great. Then I'm going to go to the blue term. Okay, so what do you call that blue term? Well, it's the first derivative term. Some people would call it the first order, okay, of the approximation. Other people would say, well, it's the second term I have to write down. Yeah, okay, call it whatever you want. It's the first derivative. And that's going to end up being this blue 1 sitting on top of 1 factorial times x to the 1. Okay, let's go to the second order term, the second degree term. Let's make this a degree 2 polynomial. Okay, because right now we've got a degree 1 polynomial here. Let's go degree 2. So this would be, in fact, let me help you out here a little bit just with some colors. This green 1 goes here, and that blue 1 goes there. The purple 1 is going to go here, so whatever you get for the evaluation of that derivative, that gets divided by 2 factorial for this second order term, and it ends up being x minus 0 squared. Probably just easier to write that as x squared. Then moving on down the road, I'm going to go and grab that red 1, whatever the derivative worked out to, divided by 3 factorial times x minus the nice number. Well, that's just 0. So x minus 0 is just x cubed, and so on. And you'd keep adding terms. And so if you want to approximate e to the x, which is a very interesting function, hey, here are some polynomials that you can use. How about this? How about 1? Well, is that a polynomial? Well, it's a pretty darn simple one. It has like 1 term to it. People would say, yeah, that's the 0th term, the 0 order approximation. Okay, let's add another term to it. Let's try to do the second part of this story, which would then just be an x divided by 1 factorial, which is actually just a 1. So now this is a degree 1 polynomial. People might call that P1, okay, polynomial degree 1, the first order approximation. And then we're going to go and add in another term. This would be this x squared term. So at this point, this polynomial has 3 terms to it. People would say it's polynomial 2. It's the second degree or second order polynomial. Okay, moving on down the road, I'd have x cubed divided by 3 factorial, and so on. I could keep adding more and more terms if I felt I needed to. Here's a little animated graphic where you can actually see the approximation kind of evolve as you go to higher and higher degrees. You know, we'll start off with just like a 1, and then 1 plus x over 1, 1 plus x over 1 plus x squared over 2, and so on, and then that ends up looking like this. So here's e to the x. And the red is the approximation, and you can see that as we add more and more terms, more and more orders or degrees to that approximation, it gets closer and closer to mimicking the turquoise graph of e to the x. And you can add as many terms as you like, right? And if you're really close to that pickup point where you were using x equals 0, you don't have to add too many terms for this to be a good approximation. All right, let's try a little bit more out here. I want to kind of compare physics and calculus. I think sometimes when we look at things across different courses, it actually is super helpful. So let's just do a little Physics 12 question. A question that in Physics 12 we never would have thought of using any calculus. It says a car has an initial position of 5 meters, so it's 5 meters from the reference point, initial velocity of 16, and it's going to continually accelerate at 6 meters per second squared. Now we're going to try to find the displacement and the location, the position, at time 4. Okay, well, I'm going to do it first the calculus way. It's going to take most of the page, and then we'll do it the Physics 11 way. And yeah, it'll only take a line or two. But first of all, the calculus way. We're going to use s for position. And so let's start taking a look at these derivatives here. If I do no derivatives at all, okay, just the 0th derivative of s, what is s at some pickup point? Let's pick up at 0. Well, they said it was 5. Okay, great. Now let's go one derivative down the road. What about s prime, otherwise known as velocity? What's the velocity at time 0? Oh, well, they told me. It's actually 16. Okay, let's go another derivative down the road. Let's do s double prime. What's that at your pickup point? Oh, well, they told me that the acceleration was 6. Okay, in fact, they went one step further. They said that it was a constant acceleration of 6. So if you're going to say that it's constantly going to be 6, then s double prime is always 6, not just at time 0. So if it's always going to be 6, then all higher derivatives are equal to 0. It can't change. All higher derivatives of s are 0. So if you were to say, oh, well, what's s triple prime, right? The third derivative of position, what some engineers would call jerk, 0. What about the fourth, sometimes called snap, 0. And then crackle, 0. Pop, 0. They're all 0, right? All of those higher derivatives. So let's see if we can now come up with a Taylor's approximation of position. What if we use just the info you gave us and said, all right, let's try to approximate the position function. We would start off with that nice green 5 and say, okay, here's the 0 order term. Then we would add on that blue 16 divided by 1 factorial, which is just a 1, times t to the first power. Then we would move on to the next term. Okay, that purple derivative evaluation was 6. Okay, so 6 divided by 2 factorial. Actually, let's keep our colors consistent here. Times t squared. It's t minus 0. I'm picking up at 0 for my nice pickup point. And then as I keep going, I'd have nothing but zeros, because all of those higher derivatives are 0. So actually this Taylor series that's supposed to go on forever, it doesn't need to go on forever. It's actually perfect by the time we've got 3 things written down. By the time we've got this degree 2 polynomial written down. It looks like it's 5 plus 16t, and then 2 factorial is 2, so 6 divided by 2 is a 3, so plus 3t squared, and the rest are all zeros. So this time, with just those 3 things written down, this degree 2 polynomial written down, we're actually perfect and ready to go. And we can figure out where this object is going to be at any time. So I might want to use this now and say, yeah, let's try this out. What is the position of this object at time 4? No problem. You would just go 5 plus 16 times 4 plus 3 times 4 squared. And I'll save you some time. That ends up being 117 meters. That's where it's located. And remember, at time 0, we were told that we should get an answer of 5. Sure enough, you do. Yep, located at 5 meters. So I know where you are. Here's your location. You're at location 17 meters. And if people are like, oh yeah, no, remember we wanted to know displacement. Oh, okay. Well, it looks like to go from location 5 to location 117, it looks like that displacement looks like that's equal to 112 meters. So yeah, I can figure out displacement and position that calculus way. The physics 11, physics 12 way, you might look at it and go, oh man, this is the way you should have done it. It's so simple. D equals VIT plus 1/2 AT squared. Sure, I agree. It's super simple. We're going to put the numbers in, and we're going to find out exactly, where this thing is, or how, at least the displacement. But what's happening here is this is actually the first couple of terms of the Taylor series. It's figuring out the displacement anyways. It doesn't have the 5 in there, and that's fine. But if you're ever wondering, like, where does this half come from? It comes from this Taylor series where we divide by this 2 factorial, right? That 2 factorial right here is a 2. And this is the acceleration divided by 2. So there's the 1/2 a. And yeah, if you wanted to, you could now go and say, okay, in this story, I've got 16 for my initial velocity, and then 1/2 of this 6, there's that 2 factorial, t squared. And if we try to put in a time of 4 seconds, if we do that, we say, okay, yeah, what's going on at time 4? Then sure, we can actually see that the displacement is 112 meters. So it gives you that value. And then you'd have to go and add on the original 5 meters to see where it's located. Okay, 2 more examples to go. Just going to try out some interesting things here for the last couple. The whole idea of Taylor series is that you can take things that are complicated, like square roots, or sine, or cosine, or e to the x, and you can approximate it with something that we feel is simpler, just polynomials. What happens if you try to get a little silly with this and take a polynomial and try to approximate it with a Taylor series? So Taylor series says, all right, I'll take whatever you're giving me and I will try to approximate it with a polynomial. And so what if you take a polynomial and say, yeah, can you simplify it? And see what Taylor will do with it. So here's my function. It's really not that complicated because it's not sine or cosine or roots. It's just a polynomial already. And so I'm going to see what Taylor would do to this if I said, hey, Taylor, can you simplify this? Let's just pick up at x is equal to 0, and we'll see what happens. So the polynomial with no derivatives is exactly what you see. 5 plus 3x minus 8x squared plus 2x cubed. And if I evaluate this 0th derivative, in other words, just the polynomial, at my nice point, so somebody's picking 0, I end up with 5. Okay, great. You know the game. Now we have to do some derivatives. Let's do the first derivative and see what we get. So first derivative would be a 3 minus 16x plus 6x squared. And if I evaluate that first derivative at 0, I end up getting 3. Okay, next derivative. Let's go and do the second derivative. I take another derivative, I get negative 16 plus 12x. And now I'm going to go and evaluate that second derivative at my nice x value. I end up with negative 16. Okay, let's go a little further. Let's go and do the third derivative. Third derivative would be 12. I'm now going to go and evaluate that third derivative at 0. Kind of a weird thing to say because it doesn't even have x's in it, but you definitely get an answer of 12. If I try to keep going, if I keep going with this thing, then all later derivatives, like if I try the fourth derivative, I get to 0. And if I evaluate that fourth derivative, putting 0 in for x, well, there's nowhere even to put it, I get 0. And this happens with all later derivatives. Okay, well, let's just see what Taylor would offer us as an approximation for this polynomial. Taylor would say, oh, okay, great, thanks for figuring out all those derivative values. Here's my approximation of your polynomial. Let's take that green 5, and then let's add on that blue 3 divided by 1 factorial times x to the 1. Oh, and let's add on some more. Let's take that purple negative 16. We'll divide that by 2 factorial times x squared. There's the second order term, the second degree term. There's the P2, as some people would call it, the Taylor series approximated with degree 2. Let's keep going. Now we're going to bring in that red 12. I'm just taking those evaluations now, putting it into that Taylor series formula, that pattern. This would be a 3 factorial, x cubed, and then all the rest were zeros. Nothing but zeros. Okay, well, let's tidy this up, because you've got those factorials there. Right? So what does this actually tidy up to? So we end up with 5. Well, 1 factorial is 1, so plus 3x. 2 factorial is 2. So negative 16 divided by 2, that's going to be minus 8x squared. And 3 factorial, that's like 3 times 2 times 1, that's a 6. So that's actually going to be a 2 coefficient plus 2x cubed plus zeros. So what happened? Well, you tried to cheat. You tried to say, hey, maybe I can make a polynomial simpler if I turn it into a polynomial. And Taylor series comes back and it says, sorry, no dice, right? So this answer we get is exactly the same as the function. Now, it would look a little bit different if we chose some other spot other than x equals 0, but it would actually be just that polynomial again, right? It's the exact same story. So you can't make something that's simple even simpler. Now, final question here. I actually grabbed this from Physics 11. So this is from Physics 11 when we were playing around with relativity and saying, hey, what happens when things go really fast and how clocks slow down? And one of the questions we kind of were wondering right away was, well, what happens if I'm just like driving around in my car around Penticton? You know, I might only be going 50 kilometers an hour. So what does the calculation look like if I try to figure out my gamma value? And it didn't work, right? So let's just take a look at why. So first of all, I would take that and convert it to meters per second. So I'm going around at about 14 meters per second. So the first thing I would do is divide by the speed of light. So I would divide by 3 times 10 to the 8 in order to find my beta value. So there's my value for beta, right? And that has to go into this gamma calculation. This beta value is very, very small. I'm going a small fraction of the speed of light. And I can square that. There's no problem squaring that number. Okay, very, very small now. And here's where my calculator runs into problems. Now, maybe not every calculator has this issue, but mine does. If I go 1 minus that, that beta squared number is so tiny that when I go 1 minus that, my calculator doesn't have the ability to keep track of enough digits to notice that it's a tiny, tiny, tiny bit less than 1. It is, though, but my calculator's lost that in the rounding. And then when I root that, of course, now all the useful information's gone because I just get a 1. And then when I go 1 divided by that, I just get a 1. And I can never figure out exactly how much the clock in my car slows down by when I drive around town, which is kind of disappointing. But if we use a Taylor series, we can actually get this to work. So we're going to lock in at a beta value of 0. Okay, that's our lock-in spot. That's going to be our nice x value. Because when you drive around town, you might as well be stopped as far as the physics is concerned. You're going so slow. So there's my function. Let's write that in a slightly different way. Let's say that f of x is equal to 1 minus x squared to the negative 1/2. And when I figure out, what is this gamma value when I'm parked at the red light? The answer is 1, right? Okay, we saw that physics 11, right? Gamma values start at 1. But I want to know, how different is it from 1 when I'm just driving 50 kilometers an hour? So you start adding some Taylor terms. Let's go and look at the first derivative. Okay, take my derivative here. I'm going to have negative 1/2, 1 minus x squared to the negative 3/2 times a negative 2x. Now I can tidy that up a little bit. The negative signs cancel, and so does the half and the 2. So let's tidy it. We're going to end up with, there's an x, bring it up to the front here, 1 minus x squared to the negative 3/2. And if I evaluate that derivative at my lock-in point, my nice point, right, this beta value of 0, I actually get 0. So you can't even do a tangent line approximation and get anywhere with this story. This graph of gamma, it starts at 1 and it starts flat. So if you ever try to approximate it with a tangent line, you just end up staying at 1. But that's okay. We know what to do now. You need to add what we would call a higher order term, a higher derivative term. So let's go until we see something that isn't 0. Let's do the second derivative. Oh, it's a product rule, right? Got two interesting things multiplied together. Derivative of x is a 1. Leave the other part. Switch the product rule up. Leave the x. Negative 3/2, 1 minus x squared to the negative 5/2 times a negative 2x. I'm not even going to bother cleaning this one up because I'm only going to use it once. If you try evaluating this second derivative at your nice spot, right? So we always have to evaluate it at this nice x value that we're working with. So we're saying, oh, well, you're almost stopped. So let's try figuring out what your derivatives look like there. If you do that with this purple one, this second derivative, the second derivative isn't 0 anymore. It's actually a 1. Okay, so let's start approximating this gamma. Right? The whole idea is that we're trying to create this approximator for gamma. We're calling it f of x mathematically. So it would be the function figured out at 0 plus the derivative figured out at 0 divided by 1 factorial times x to the 1. And I'm going to go as far as the second derivative figured out at 0 divided by 2 factorial x squared. Okay, so approximately f at 0, well, that was that green one. Then we end up with a 0 for that blue part. So you'd actually end up with plus 0x. Well, that's useless. But we know how to add the next order term. Okay, and I'm going to grab that purple term. So it would be this purple 1 going here divided by 2 factorial. Well, 2 factorial is just a 2 times x squared. So I would have plus 1/2 x squared. Now there are more terms, but if you only want to grab the first term that isn't a 0, okay, after the original term of 1, then you could say, hey, here's a way to approximate what gamma is in your car when you're going really slow. It's going to be 1, we already knew that, plus 1/2 x squared. Now, you sort of have the same problem when you go back to your physics story, right? So that x is equal to beta. If you're to say, yeah, okay, can I try this out again? You know, what were we doing? We're doing about 14 meters per second, roughly. If I put that in to my calculation of beta, I'd have to divide by the speed of light. Okay, that's the physics to it. So there's my x value. Now, if I try to say, hey, calculator, I've done this Taylor thing, help me out here, find the gamma for my car, I still run into problems, right? If I go 1 plus 0.5 times that answer squared, I still get a 1 because the numbers are so small that are being added onto the 1. But maybe just don't add the 1 on. How about we do this? We can go, okay, what is your beta value? There's your fraction of the speed of light. Let's just look at the interesting term. Let's look at the extra little bit, because that's what we're kind of worried about anyways, right? Like how much extra time do we add or lose with this relativity story? So you could go 0.5 times that answer squared. There's the part that gets added to the 1. So we now know what the gamma looks like. It's 1 decimal and then 14 zeros and then a 108. Okay, at least to that second order approximation. So that's a way that you can actually access things that your calculator wasn't even capable of doing. And so we're going to stop there. That's the end of the story for the Taylor series, where you can actually use just a sequence of polynomial terms to approximate some really complicated functions. The whole idea is to try to make your life simpler. I know it might look a little bit messy, but the whole idea is that by adding more and more terms to this polynomial, you can actually do a decent job approximating any function you want.